In this video, I will explain the basic principle of CIGS solar cells and how they are manufactured. Here's an example of what everyone thinks of when the word solar panel is mentioned: commercially used silicon solar panels. A solar cell is simply the component that is put in an array to make up a whole solar panel. Let's take a look inside of one. This is a basic cross-section of a silicon solar cell. It includes the p-type and n-type materials, which form a p-n junction where voltage is produced, the rear and front contacts for connection of a load, and an anti-reflective coating to allow for the most efficient absorption of sunlight possible. Now let's see the solar cell in action by hooking up a bulb to its contacts. Sunlight in the form of a photon enters the cell where the p and n-type materials are joined. This causes an electron-hole pair to form. The electron then flows through the n-type material through the wire and causes the bulb to light up. It then recombines with the hole, completing the circuit. The constant flow of photons hitting the cell will therefore cause a constant flow of current, allowing us to power electronics. Next, I will describe a type of solar cell that is currently being researched named CIGS, standing for copper, indium, gallium, selenide. It is classified as a thin film solar cell, and although the layers don't seem thin on screen, they are 50 to 100 times thinner than a silicon cell. The main layers pictured here are the glass, molybdenum serving as a back contact, CIGS as a p-type material, cadmium sulfide as an n-type material, and zinc oxide acting as a transparent conducting oxide, making the absorption of photons as efficient as possible. Keep in mind, all these layers of material may seem like a lot, but altogether this cell is only 1/10 the diameter of a human hair. However, in order to construct a functioning CIGS solar cell, several advanced machines must be used to deposit each layer. A thermal evaporator carries out deposition using heat. It can deposit multiple elements simultaneously because of its numerous compartments, making it useful for the CIGS layer. A sputtering machine deposits material by creating a gaseous plasma and then accelerating ions into the target material. This in turn ejects the material, causing it to accumulate on the cell above. An E-beam evaporation machine utilizes an intense electron beam, steered with electric and magnetic fields to hit a source material. This vaporizes the material and causes its atoms to deposit on the cell above. The image to the right is the element niobium in an E-beam machine being deposited to glass. The light from the intense beam hitting the metal is actually so bright that it is not safe to look at directly without eye protection. All of these machines help to manufacture the final product, a CIGS solar cell. Following completion, the cell is tested for efficiency and other measurements for further research. The main reason CIGS cells are currently being researched is because of their super thin physical quality and easy manipulation of material concentrations. If CIGS cell efficiency can surpass silicon, countless technological advances will be made. Put simply, CIGS has the potential to revolutionize the solar energy industry.